Alright, so there are several ways you might try to define performance, and the thing is, people try to scale it to suit their systems, right? So um, there has been few standards or few ways, and the whole point of this part of the course is to just rationalize why it should be this way and not any other way, which a manufacturer will try to do. So you realize that so a computer system is all he's thinking about is the response time, but someone at maybe the computer center manager will be thinking about throughput. As depending on different characteristics people expect from the system, they may rate the performance differently, right? However, at the very core, very raw definition of performance, and performance is just 1 over the execution time, right? It's inversely proportional to the execution time. The smaller your execution time, the better your performance. Now, you can have performance as a ratio, right? That is if you compare two CPUs or two computers. So, performance of X against performance of Y may give you some value N, right? Which means that X will be N times faster than Y if N is greater than 1. Now, if it is less than 1, it's still the same sense, but I mean, in terms of logic, it's a bit skewed. So there are several ways you can improve performance, and usually it comes from questioning yourself, what should I improve? Should I add more CPUs or faster CPUs? Now, the question will be answered later in the course, but it's all a point of um, making the analysis first, right? Now, you can consider it from a very high level value. For example, if you consider giving it fast CPU, you realize that you have a better response time and a better throughput, right? You can execute more instruction. The CPU is faster, so you have to wait less between jobs. However, if you add CPUs and that is for the old CPUs, you add more of it. Well, you have a better response time, maybe, right? And you have a better response time, maybe, but your throughput will increase, right? So it's a matter of the judgment at the moment. Now, performance comparison. This is about a point where you may need to be able to make a statement and compare the performance of two pieces. So, for example, we found that the execution time of a program A is 10 seconds and that will be 15 seconds. Now, you can find the performance measure, right? And it's as simple as taking the ratio of I would usually like you to take it the ratio of the bigger execution time over the smaller execution time so that it can make logical sense. It doesn't matter how you do the ratio, right? It just matter how you are able to come up with the interpretation. So you realize that B has the higher execution time, so it has a low performance than A, right? So you realize that it gets 1.5, which means that A is 1.5 faster than A. That's one way to say it. Now another person will say, oh, A is what 50% faster than B, right? So A is 1.5 times faster than B, or it's what 50%. How did they get a 50%? Well, the total performance is measured over a factor of 1, right? And I have 1.5. Now, if you want to find the excess increment, you just subtract 1, then multiply by 100, right? Now, this one will give you 50%. You can try using your calculator. And there is actually a whole performance equation, right? To make performance not as skewed as possible, right? So performance in terms, assuming we are both executing the same program, right? Then we have to adjust performance in terms of the seconds per the program. So, and that can be equivalent to the cycles per program in the seconds per cycle. You realize that the more you look at it from a high level overview, the more you are possibly making a biased judgment, right? Now, this formula is actually equivalent to this, right? So you realize that the cycles per program, the cycles actually refers to the CPU, and the seconds per cycle is actually, the clock is actually called the clock cycle, right? So that's what you see in most machines. So to improve performance, there are a number of ways, and it actually gives rise to the notion of, um, what to improve, right? So you can actually reduce the number of cycles for the program, or reduce the clock cycles, or increase the clock rate, right? Each one of them will have its way of increasing performance. However, usually there is a cap on some of them, how much you can increase. So it's not like you can increase it forever. Now, we are trying to rationalize, um, how many cycles are required for a program. Now, you realize that you can assume time to be just a linear something, that each instruction takes the same number of cycles, right? But in the real world, that's incorrect. Some instructions actually are more intensive than the others, so they take more cycle time than the others, right? And if you're unfortunate and you have something like, a single cycled, CPU, right, where you are trying to make all the instructions take the same time, you realize that you'll be wasting much of the time. Now, if you have a multi-cycled CPU where you are trying to make the instruction take, um like, or every single instruction take like small amount of the time, you realize that some instruction will take more cycles to complete than the others, right? So there is a disadvantage on both sides. But, um that's that for that. But you realize that there are some instructions like multiplication, it takes more time than addition. Floating point operation takes longer. Then important point is changing the cycle time often changes the number of cycles for various instructions, because it means changing the hardware design. This is what it means. Now, if you are some way somehow able to change the cycle time is the time it takes for a clock cycle to be completed, right? If you're able to change it some way somehow, right, then, one way or the other, you've been able to make improvements on all levels, because you realize that for the other elements which affect the CPU time or the execution time, you realize that tweaking one of them will somehow affect the other, right? But if you're able to change it from the very lowest point, that is the cycle time, the time taken by the clock, you have been able to improve all the way throughout. So we'll see an example of that. But, we'll take a look at few vocabulary so that you don't get confused as you are mentioning different vocabularies. So, for example, there is a vocabulary known as the cycle time. That's the second per a cycle. There's another one called the clock rate. That's the cycles per second, right? Now, someone asks, is the cycle time not the same as the clock rate? No. The cycle time is the seconds per cycle. So, for example, for your CPU or your machine you are using, right? Um, every clock cycle, right? How long does it takes, right? Every clock cycle. Now, usually most machine, the cycle time is actually, for example, a single cycle CPU is actually capped by the longest instruction, right? For most single cycled, CPUs. So the cycle time is capped for the most longest instruction. So for example, if the most longest instruction is a load word instruction, the cycle time will intentionally be made to be the time for a load word instruction. However, the clock rate is the cycles per second. That is, for each seconds, how many transitions does your clock, make? Now, this one is usually only capped by the hardware, right? You can increase it to a particular limit. From there, you can't do much. Now, there's one last part called what CPI. That is the cycles per instruction. So the CPI takes into account that different instructions have different number of cycles to execute, right? Now, there is one last form of performance measure, which we call the Mips, right? And it's called millions of instructions per second. Now you realize that it will be higher for a program using simple instruction, and we'll see an example of that. So uh, now there is a whole equation for performance using the previous terms we've realized, and this is less biased, right? Because it considers from the compiler side to the architect side to the computer programmer side, to the designer side, right? Compiler to the architect to the designer side, right? And it is less biased. So that's the equation you see. Now, it's possible to derive the performance equation from here, but I think you can leave it as an exercise or something like that. So you realize that for any of the elements you take, right, it is dependent on a very common parameter. For example, if we are executing two programs, right, you can say that, hey, my PC is faster than yours because it can execute more instructions per program, right? Now, we won't know the difference unless we have also considered the number of cycles per instructions and the time per cycle, right? So my PC may be terrible because, hey, I actually take more time per each cycle, right? And it will be a hardware issue, right? Not from the code side issue, right? So it's a matter of how biased the the performance judgment is, right? Now there are more performance factors, and they they have different determinants, and those are what I stated here. Now there's one more performance measure, and I said would take note of it, right? And it's called the Mips, right? So the Mips, it's just the instruction count over the execution time times 10 exponent 6. Remember, the 10 exponent 6 is in the denominator. Now, one person can derive it and realize that it is actually the clock rate over the CPI times 10 exponent 6 is an assignment you can just try to derive and see, or the video will be extra long. So that's what we realize makes it, right? But I realize that even with this one, which is taking note of the clock rate and the CPI, it still has a very high, it's still very biased, right? Because why? Let's see. So for example, with this Mips something we just talked. Now, if you have a floating point hardware, right? Now you realize that a floating point operation takes a lot of clock cycles to operate without the floating point hardware, right? Without the floating point hardware, you may be taking 50 single cycle instruction, right? At a clock rate of say 1 megahertz. Now, with a floating point hardware, you may be taking one two cycle instruction at the same clock rate. Now, what does it mean? You realize that in the first scenario, right, you are still using a single cycle instruction. So your CPI is the same, right? But in the second scenario, you are using a two cycle instruction. You are using one two cycle instruction, right? So you realize that your CPI has kind of increased here. Now, from a very normal perspective, you'll quickly realize that, oh, the floating point hardware is better than the one without the floating point hardware. But let's go and see the mixed perspective. The mixed perspective says take the clock rate divided by the CPI, right? Now, what is the clock rate? Now, because you are still using the same machine, the clock rate is still 1 megahertz, right? So it's 1. What's the CPI? The CPI is the clock cycles per instruction. The question said you are using single cycle instruction, right? So it means that each instruction takes what? One clock cycle, right? So 1, right? And you put your 10 raised to the power 6 here. Now, when you do this, I think you get 1 MIPS, right? So you get 1 million of instruction per second. That's what Mips is saying. Now let's consider the second part. The second part says now you are instead of using 50 single cycle instruction, you are using only one instruction, and this instruction is what is a two cycle instruction, right? Now this is what it means that it is one instruction. That instruction takes two cycles to complete, right? The first one was one instruction and it took each instruction took one cycle to complete, but you needed 50 of them to do the floating point operation. The second one is you need only one instruction, right? But that one instruction will cost you two cycles. However, MIPS in MIPS calculation, you realize that you come and do the clock rate, which is one. Now the CPI, before you realize the CPI will be what two. The instruction is one, and you need what two cycles, so two cycle per one instruction, so two. Now when you multiply by 10 with the power 6, and remember the clock rate is in megahertz, so here's also 10 raised to the power 6. So they kind of cancel and everything. Now this one will give you 0.5, right? 0.5 MIPS. 0.5 MIPS. Now you realize why MIPS is terrible, right? 0.5 MIPS. Realize that in the first one, although we are doing terrible, realize that MIPS says we'll be doing 1 million of instruction per second. The second one, although we have improved the hardware, Mips says we are doing what 0.5 million instructions per second. We have actually reduced, but that's not the case, right? And the reason is simple. We did not take into account the number of instructions. If we are taking into the account the number of instructions we are taking, we were, um, we were executing at both end. It would have reviewed it. And so that's the um, problem of MIPS, right? So, and that's actually the explanation you see here, right? So it says it ignores the problem, and most people actually use MIPS to actually quote peak performance, right? That's why I say the whole thing is biased. You have to take note of it. So that's it. There are also other metrics, M flops, and relative MIPS and normalized MIPS. Is they all actually add to confusions, right? So basically, most questions would actually give you a means to determine the metric to use, right? And as you solve those questions, you would see that. So